Okay, in this problem, we're looking at this non-relativistic theory that we're going to quantize. But first, he wants us to work out the equations of motion, the Hamiltonian, some other stuff. So for this Lagrangian, it's not particularly difficult to do any of those things. The only difficult thing about this is that it's been so long since we've used some of these formulas that you have to go and refresh your knowledge of them. But once you do that, they're not particularly difficult to work out. So interestingly, the equations of motion you get are the Schrodinger equation, and then the energy momentum tensor. Most of the Lagrangians we worked with before were relativistic, so symmetric in time and spatial derivatives. So you could compute t mu nu, kind of just immediately from this expression. Here, since we don't have that symmetry, we have to compute the spatial and time parts separately. So I've done that here. That's what I get. And then the Hamiltonian we can just write as the integral of the 0, 0, 0 component of the energy momentum tensor, integral over all space. And then lastly, we want to work out the conserved quantity associated with this internal transformation. And again, we've done exactly this thing before. So, I'll just scroll through here. You can see what I've got. But yeah, so we've done all this stuff kind of before. But on to the more interesting part of quantizing this theory. So we kind of enforce this commutation relation between psi and its conjugate momentum, which reduces to this expression. And then we, since our Lagrangian is first order and time derivatives, that leads to us being able to expand our operators just in terms of one set of creation and annihilation operators, as opposed to how we did things before with the complex scalar field using a B and a C. So there's no antiparticles in this theory. And so once we've done that, we can verify that our commutation relation holds. Again, the easiest way to do that is just to write this out and then enforce the usual commutation relation between our raising and lowering operator, and we get what we want. And the last thing is, so the Hamiltonian, we have this expression for it, so we plug in our expressions for our fields. Again, it's just an easier version of what we've done before. And what we get in the end is just like the Hamiltonian we had for the Klein-Gordon field, only instead of an EP, AP, we have p squared over 2n, AP. And so if we work out the commutation relation like we did before, instead of the EP, the commutator of H and A dagger, instead of EP A dagger, we get in this case, q squared over 2m A dagger. And that enables us to find the energy of our one particle states, which in this case, we don't have to worry about relativistic normalization, so we just define our one particle states like this. And using our commutation relation, we can easily find that the energy of a one particle state with momentum q is just q squared over 2m, which is the energy of a classical free particle.